Hello, everyone. First of all, as an organizer, I would like to thank all of you for participation. Without you, it wouldn't be possible for us to organize the symposium and the program. Well, my mentee is İpek Yağmur. She is a third year undergrad student in Gazi University. Actually, we couldn't study a lot together because in the midsummer we had to change the mentor, but we made a great progress. Today, she is going to talk about somehow the algebraic proof of the fundamental theorem of algebra. Take the lead. Yeah.
Hello, everyone. First of all, I'm very happy to be part of this event, and I would like to thank the organizers and my mentor for. So we were working on the algebraic proof of fundamental theorem of algebra.
Oh, just good.
Here's my outline. First of all, I will give you the fundamental theorem of algebra. Then, before the proof, I will give you some of the information that we use for the proof, like ring and field and some of the extensions. So let's start with the theorem. The field C of complex number is algebraically closed. Equivalently, if P of Z is a non-constant polynomial over C, then there exists Z that's 0 in C such that P of Z 0 is equal to 0. And let's start with the rings. A ring R is a set together with two binary operation, addition and multiplication, satisfying the following X. First of all, R with the addition is an abelian group, and the second one is set R is closed under the multiplication operation. That means for all A and B in R, A times B in R. And third one, X is associated. That means we can change the parentheses under multiplication. The fourth one, the distributive rows called in R. That means dispersive property of multiplication upon addition from left and right. And we call the ring commutative if the multiplication is commutative. The field. A field F is a commutative ring with the identity in which every non-zero element has the inverse. Equivalent to the set F to the star is equal to F minus 0 of non-zero element of F is an abelian group under multiplication. And subring, a non-empty subset S of the ring R, subring if S is closed under addition, multiplication, and the additive. There is A and B in S, then A plus B, A times B n minus A are also in S. And subfield, let F be a field, then S is subgroup of S, the non-zero subgroup of F. It's said to be a subfield of F if for all A and B in S, A minus B in S, and for all A in S and non-zero B in S, A times inverses of B in S. And here's an example. The set of all A plus BI for A, B, and Z, the subring of C, but not a subfield. Let's take R set consists of A plus BI, and let's take X to be A plus BI and Y to be C plus BI. Then the X plus Y and the minus X, and also the X times Y in R, and the conditions for subring are relevant, as you can see that. However, 2 is element of R, but the multiplication inverses 1 over 2 is not element of R, so R is not a subfield. The characteristics of a field. Characteristic of a field F, denoted by this, as define it to be the smallest positive integer P such that P times identity is equal to 0. If such a P exists, and if define it to be 0 otherwise. And the number of elements in a finite field K is called order of K. And the theorem, if any field F, all non-zero elements have the same additive order, this is called the characteristic of F is said to be zero if all non-zero elements have the same order. Let's give an example. For every positive prime number P, there are P element fields. For example, the characteristic of the field that P is a P. Let's Z P is consists of 0 bar, 1 bar, 2 bar, all the way up to P minus 1 bar. And if we get 1 bar to 1 bar added cells is equal to 2 bar. And now if we consider 1 bar adding its cells like 2 times, it's equal to P line is equal to 0 bar. So the characteristic of the field Z pi is and the characteristic of a field is equal to 0 because if you take one edit and edit its cells like a certain finite number of times, then you just go get bigger and bigger in the reals. So there's no finite number of times that you can get 0 back again in the reals. So the complex numbers are just even bigger than the real numbers. So it's same for the extension. Field extensions. If K is a field containing the subfield F, then K is said to be an extension field of F, denoted by this or by the diagram. If F is a field and E is a field extension of F, then the identity of E and F are the same. From this theorem, we can express the result that the identity of field F is also identity of all subgroups of F, subfields of F. If K over F is any extension of fields, then the multiplication defined in K makes K into a vector space over F. In particular, every field F can be considered as a vector space over its field. The degree or relative or index of a field extension K over F, denoted by this, is the dimension of K as a vector space over F. The extension is said to be finite if the degree of the K over F is finite and is said to be infinite otherwise. And examples, the minimum polynomial for square root of 2 over Q is x squared. And because of that, square root of 2 is of degree 2 over Q. Hence, the degree is equal to 2. Dimension of Q cubed over Q is 3 because this vector is the basis. More generally, if F is a field, then the F to the n is n dimensional vector space over F. And the degree of the C over R is equal to 2, since the 1 and I is the basis of C over R. On the other hand, the extension field R of Q is an infinite dimensional vector space over Q. And the algebraic and the transcendental. The element alpha is said to be algebraic over F. If alpha is root of some non-zero polynomial f of x, the polynomial ring over F. If alpha is not algebraic over F, the alpha is said to be transcendental over F. The extension K over F is said to be algebraic if every element of F is algebraic over F. The example, in the extension field C of R, I is algebraic over R because it's the root of x squared plus 1 in Rx. You can easily verify that the element 2 plus I of C is the root of this polynomial in Qx. Thus 2 plus I is algebraic over Q. Similarly, the fifth root of 3 is algebraic over Q since it's the root of this polynomial. And the other example, every element C in a field F is algebraic over F because C is the root of C plus X plus C in Fx. And the real numbers pi and e are transcendental over Q. But we immediately point out that since the pi is the root of the polynomial x minus pi, then is algebraic over R. The definition, an extension field K of a field F is said to be an algebraic extension of F if every element of K is algebraic over F. Example, if A plus bi in C, then A plus bi is a root of this polynomial in Rx. Therefore, A plus bi is algebraic over R, and hence C is an algebraic extension of R, but not an algebraic extension of Q, since there are real numbers such as pi and b. They're not algebraic over Q. Splitting field. Let K be an extension field of f and f of x, a non-constant polynomial of the degree n in f of x. If f of x factors in kx as follows, then we say that f of x splits over the field f. The definition: if f is a field and f of x in polynomial ring over f, then an extension field k of f is said to be a splitting field over f, provided that the one f of x split over k, and two, k is equal to f with u1, u2, all the way up to un. Example, if x squared plus 1 is considered as a polynomial in Rx, then C is a splitting field, since this polynomial can be factored as dx. C is equal to R with I. Similarly, Q with square root of 2 is a splitting field of the polynomial x squared minus 2 in Qx. An algebraic extension field K of f is a normal, provided that whatever an irreducible polynomial in f of x has one root in K, then it splits over K. That is, all its roots are in K. The theorem: the field K is said to be splitting field over the field f of some polynomial in fx if and only if K is finite dimensional normal. Example, the field Q with cube root of 2 contains the real root cube root of 2 of the irreducible polynomial x cubed minus 2 in Qx, but does not contain the complex root cube root of 2 plus times omega. Therefore, Q with cube root of 2 is not the normal extension of Q, there hence cannot be the splitting field of any polynomial in Qx. The algebraic closure: a field over which every non-constant polynomial splits is said to be algebraic closed if K is an algebraic extension of f and K is algebraic. K is called algebraic closure of f. The example: since the field of complex number is an algebraic closure of the field of the real numbers R, in that we know from the fundamental theorem of the algebra that if f of x is a polynomial of positive order, then the polynomial f of x has a root in complex numbers. Because of this theorem, C is an algebraic closure. Since R is a subset of C, C is an algebraic closure of R. Separability: let f be a field, a polynomial f of x of degree and is said to be separable if it has n distinct roots in some space field. If K is an extension field of f, the real element u in K is said to be separable over f if u is an algebraic over f and its minimal polynomial p of x and fx is separable. The extension field if K is said to be a separable extension if every element of K is separable over f. Thus, a separable extension is necessarily algebraic. Example: the polynomial x squared plus 1 in Qx is separable since it has distinct roots I in minus I in C. But the polynomial is not separable because it factorizes as like that. Hence, f of x has one repeated root and the total of the three distinct roots. Galois: let K be an extension of field of f, and f isomorphism of K is an isomorphism. It contains K to K that fixes f element-wise. The set of all f isomorphisms of K is denoted by f, and it's called the Galois group of K over f. The Galois extensions: if K is a finite dimensional normal separable extension field of the field f, we say that K is a Galois extension of f, or that K is Galois over f. Now, I'll give you some of information about the proof. So let's continue. our assumptions are going to be as follows. So zero assumption is that finite field extension are continuity of field of characteristic zero. I'm just gonna use characteristic zero because it makes it easier and is the only case I know. The first assumption is any polynomial in real with real coefficients of odd degree has a root in reals. And two, C has no extension of degree 2. Equivalently, every element of C has a square root. Because we are working in characteristic zero. And now we're just gonna use this two assumption 1 and 2. And we'll look at now R containing C containing X. And let X be any finite normal extension of R containing C. Now to show C is algebraically closed, it's enough to show X is equal to C. Because if C wasn't algebraically closed, we will be able to find a non-trivial normal extension. And X is finite and normal and is also separable because we're working on characteristic zero. So X over R is separable and normal. So it's Galois. And let's put G to be Galois group. It's going to be some finite group. So now the idea is to translate to our conditions, the condition about the Galois group G. So we know that subgroup of G corresponds to an intermediate subfield of X. So our first assumption said that any polynomial in of odd degree has a root in reals. And on the other hand, there is no extension of odd degree of R apart from the trivial one. So we can say that any subgroup of G of odd index is just G. So our degree of the extension over R is actually the index of the corresponding subgroup, not the order of subgroup. So our two assumption is say that the C has no extension of degree 2. So suppose H is a subgroup corresponding to C, and let's take H to be the Galois group X over C. Then the automorphisms of X fix in all elements of C, and the extension of C is correspond to subgroup H. So H has no subgroup of index 2 because we said that C has no extension of degree 2. And so we say that the G has no subgroup of index 2, and H and G has H containing G has no subgroup of index 2. Now we want to show that the H is trivial. So let's pick a slope 2 subgroup of G. This has odd index by 1, and it's all G. So G has order 2 to the n for some n, and H has order 2 to the n for some n. So H is nilpotent because for the nilpotent, any group of prime power order has the theory nilpotent group is that if H has a greater than 1, have an order greater than 1, then H have a subgroup of index 2, and so we look at the 2 to the n for n greater than 0. It has a subgroup of index 2. So H can have a subgroup of index 2. So if the order H is equal to 1, hence there are no extension of complex numbers. Here's my references. Thanks for it.